Hello, everyone. In today's lesson, we will study proportional operation circuits, Part 1. Our learning will cover the following topics. Let's begin with the first part, basic circuit. As shown in the diagram, we have an inverting amplifier. The input voltage Vi is applied through R1 to the inverting input of the op-amp. R2 feeds the output signal back to the inverting input, forming negative feedback, while the non-inverting input is grounded. Amplifier characteristics. Voltage gain. From the principle of the virtual short, we know Vn is almost equal to Vp equals 0. From the principle of the virtual open, we know Ip is almost equal to In is almost equal to 0, hence I equals 0 and I1 equals I2. Therefore, Vi minus Vn divided by R1 equals Vn minus Vo divided by R2. This leads to AV equals Vo divided by Vi, which equals negative R2 divided by R1. The negative sign indicates that the output voltage Vo is 180 degrees out of phase with the input voltage Vi. The voltage gain depends only on the resistors R2 and R1. When R2 equals R1, the circuit becomes a simple unity gain inverting amplifier, in which Vo equals minus Vi. Input resistance and output resistance. The input resistance is the equivalent resistance seen from the input terminal. Since Vn equals 0, we have Ri equals Vi divided by I, which is Vi divided by Vi divided by R1, resulting in R1. The input resistance of an inverting amplifier is much smaller than that of a non-inverting amplifier. Similar to the non-inverting amplifier, the output resistance of the inverting amplifier is approximately 0. From the principle of the virtual short, we know Vn is almost equal to Vp equals 0, so the inverting input terminal is at a potential close to ground. This is called a virtual ground. The existence of the virtual ground is an important characteristic of the inverting amplifier operating in a closed-loop state. It means that there is essentially no common mode voltage at the two input terminals of the op-amp, which lowers the requirements for the op-amp's common mode rejection ratio, CMR. In contrast, for a non-inverting amplifier, Vn is almost equal to Vp but not equal to 0, indicating that the op-amp has a non-zero common mode input voltage. However, when the CMRR is close to ideal, the output voltage is very small and can be neglected. In other words, the non-inverting amplifier places higher demands on the op-amp's common mode rejection ratio. Example problem: replace the resistor R2 in the circuit with a T-network. 1. Find the closed-loop gain of the circuit. 2. Given R1 equals 51 kiloohms, R2 and R3 both equal 390 kiloohms, and Vo equals negative 100 times Vi, calculate the value of R4. 3. If the T-network is replaced directly by R2, and when R1 is 51 kiloohms and AV is negative 100, find the value of R2. Solution. 1. Using the ideal op-amp assumptions, Vn is almost equal to 0 and In is almost equal to Ip is almost equal to 0. Write the current equations at nodes N and M. II equals I2, I2 plus I4 equals I3, that is, Vi minus 0 divided by R1 equals 0 minus V4 divided by R2, 0 minus V4 divided by R2 plus 0 minus V4 divided by R4 equals V4 minus Vo divided by R3. The closed-loop voltage gain is AV equals VO divided by VI equals negative R2 plus R3 plus R2 times R3 divided by R4 divided by R1, which equals negative R2 divided by R1 times 1 plus R3 divided by R2 plus R3 divided by R4. 2. By substituting R1, R2, R3, and R4, we can find that R4 equals 35.2 kiloohms. 3. When replacing the T-network directly with R2, R2 equals negative AV times R1 equals 100 times 51 kiloohms equals 5,100 kiloohms. The value of R2 reaches as high as 5.1 megaohms, which introduces significant noise and makes the circuit more susceptible to interference. Simply reducing the values of R2 and R1 proportionally cannot meet the circuit's input resistance requirements. Using a T-network, however, allows the use of lower resistor values R2, R3, and R4 while achieving high gain. This configuration can be used as a microphone preamplifier. Compared to the non-inverting amplifier, whose gain equals 1 plus the ratio of the feedback resistor to R1 and whose output is in phase with the input, the inverting amplifier has a gain equal to the negative ratio of the feedback resistor to R1, with the output phase inverted relative to the input. Both gains are determined solely by the ratio of external resistors and are independent of the parameters of the integrated operational amplifier. That concludes today's lesson. Thanks for watching. Thank you.